Okay, so welcome to the first session, or the first parallel session of QIP. It's a pleasure to sort of introduce sort of the first of our three speakers that we have today, which is Yingkai from University of Sheffield, who will speak to us now about his work on constructing quantum codes from a classical code and how this also relates to local Hamiltonian. So please go ahead, Yingkai.
Thank you, David, for the introduction, and thank you all for tuning in to this virtual QIP. So I'd like to tell you about my work on constructing quantum codes from any classical code and embedding in the ground space of local Hamiltonians, which is the joint work I have with Ramis. And this talk can be divided into two parts. So the first part is where we introduce a new framework that takes any classical code to a quantum code. And in the second part of the talk, we're going to introduce linear distance quantum codes in the ground space of a new two-local Hamiltonian. So there are many ways to construct quantum codes. One of the most celebrated formalisms in which we construct quantum code is the CSS Formalism, which needs no introduction. And this has later been generalized to the stabilizer and later codeword stabilized formalisms. So this work fits somewhere in the intersection of these previous coding formalisms. We encompass all CSS codes. We don't cover all the stabilizer and codeword stabilizer codes, but we do fall outside of the framework. So this is a new framework, as you will see in a bit. So I'd like to begin by explaining how we can design a logical qubit using any classical code. So let us begin from any classical code C. So this classical code has no a priori restrictions on its structure. It doesn't have to be linear. It doesn't have to be additive. It's just a set of symbols over some alphabet. And so what we're going to do is we're going to partition this classical code into two sets, C0 and C1. And we're going to construct a superposition over the code words in C0 and call it the logical zero. And we're going to make a superposition over classical code words in C1 and call it the logical one. By construction, the 0 state and the 1 state are orthogonal to each other. And as you can see over here, what is unspecified as yet are the coefficients in this superposition. And for the moment, we're going to say that it's going to be non-negative. And it is quite clear that if we set the classical code's distance to be d, the bit flip type of distance for this quantum code with the logical code with 0 and 1, it will have a bit flip distance also of d. But what is not so clear is how it can also correct the phase errors. And this is what I would like to explain. So in order to verify that a quantum code can correct errors, we need to go back to the quantum error correction criterion. So back in 1997, Neal and Laflamme introduced a set of conditions from which one can easily check if a quantum code can correct set errors. So in our talk, we're interested to design a quantum code with a minimum distance of d, which means that it can correct up to half the number of errors in the distance. So the quantum error correction criterion can be written in this matrix form. Here, pi, this capital pi, is the code's projector. And for the special case in which we're considering, which is the encoding of one logical qubit, pi is very simple. It just has a logical 0 component and a logical 1 component. So in order to check that this quantum code has a distance of d, all that we need to check is that pi p pi is proportional to pi for any Pauli that has a weight of at most d minus 1. And as you can see, in the simple case when pi has this form, we can just rearrange this matrix equation and get these scalar quantities over here. And the first scalar equation is what we call the non-deformation conditions, because really the zero sandwich is the same size as the one sandwich. I call these sandwiches. So what's in between the sandwich is the Pauli error that we want to check. And we also want some orthogonality conditions. That is, by putting the P on the logical one, it doesn't take it to the logical zero. And this orthogonality condition comes for free from the classical distance of the code. So what we really want to check is how can these non-deformation conditions be satisfied by an appropriate choice of the coefficients in the superposition for our logical code words. And before we go into that, let us see what type of Pauli errors we need to consider. Now, consider the case in which your Pauli error, the Pauli matrix, this is a multi-qubit Pauli matrix, it has some non-diagonal terms in its tensor product. In that case, that Pauli will, this sandwich will evaluate to zero, because once the Pauli is non-diagonal, it will take a classical code word, the computational basis state, to some other state, and there will be some offset, and it will evaluate to zero. So anyways, the non-diagonal Paulis will all evaluate to zero, and so for the non-diagonal Paulis, the sandwiches, the non-deformation condition is satisfied automatically. So thus, it suffices to only check the non-deformation conditions for the diagonal Paulis. And when we have the diagonal Paulis, the sandwiches can be evaluated quite simply. One can appeal to the fact that the diagonal Paulis do not change the, preserve the computational basis states. And so each of these sandwiches is just a convex combination of these, what I call the code word sandwiches. So the zero sandwich is a convex combination of the code word sandwiches, and similarly for the one sandwich. So, and recall, all that we need to check for the encoding of one logical qubit is that the zero sandwich is equals to the one sandwich. Writing this in linear algebra terms, this basically means that we want the zero sandwich minus the one sandwich to be equals to zero. And this means that we want this an appropriate convex combination of these code word sandwiches to be equals to zero. So what we do is that we collect these code word sandwiches into a matrix A, and we call this matrix A. And we want this matrix to be real. And because we want this matrix to be real, we can take the real and imaginary part of these code word sandwiches, because in general, the Pauli, this Pauli is not just a qubit Pauli, it can be a qubit Pauli, and it could have some complex phases. And what we end up finding is finding a real non-zero solution of this matrix equation, AX equals to zero. And from the solution X of this matrix equation, we are going to derive the coefficients from which we design our quantum code. So recall the A coefficient over here is for the logical zero, and the B coefficient is for the logical one. So from the positive values of X, we're going to make the logical zero, and from the negative values of the X, we're going to make the logical one. And so this is the recipe. And so we can see that we will always have a non-zero solution to this equation when A has a non-trivial null space. So, so the problem of designing a quantum code is equivalent to that of finding a solution of the null space of this matrix. So an obvious implication is that from linear algebra, we know that if we have a matrix that is wider than its tall, then it must have a non-trivial null space. So, and in this matrix, the columns are labeled by the classical code words, and the rows are labeled by the diagonal Paulis. So what this means is that if we have enough classical code words that we choose, and that is much greater than than the volume of this Hamming ball of radius d-1, then we can have a quantum code. And so this brings us to our first main result, which is using any non-zero solution of this homogeneous matrix equation, we can derive a quantum code. And a simple, easy to remember formula is that as long as we have a huge number of classical code words, which is larger than twice the Hamming volume of, then you can have a quantum code of prescribed distance d. So the next question is, well, now we can see how we can encode one logical qubit. But can we have more than two logical code words? We like to embed more logical code words in our quantum code in general, not just two. So now let us revisit this A matrix again. So let's suppose that we have a huge number of classical code words in our A matrix, and and then we partition this, we partition the classical code into subcodes, C1, C2, C3, and so on. So the classical code C1 and C2 will correspond to the original construction. So the union of C1 and C2 can imagine that we've already found the first and the second logical code word. So so recall previously that we just needed to check the condition AX equals to 0. And if you chop up this matrix into block form, this will be equivalent to A1, A2 times this X, where you chop the X into the positive and the negative parts. You want this to be equals to 0. Okay, so this is what we had from before, written in this block form. Now we want to apply the same idea to design the additional logical code words, say the third logical code word. So for that, we will take the second and the third piece of this A matrix, and we want to check this similar condition, except that over here, X1 is already fixed. And X2 is something new that we want to solve for. And from this X2, we're going to take the square roots of it to form the probability amplitudes of our logical 2 code word. And so all that we need to do is to solve this matrix equation subject to this non-negative constraint. This is just equivalent to the feasibility problem of a linear program. So for the finding of the additional logical code words, we just need to check the feasibility of these of a sequence of linear programs. And this can be done using any algorithm for checking feasibility of linear programs. Of course, we can use this very nice paper by Dice in Annals of Mathematics in 1926 that constructs the non-negative solution if it exists analytically. And using this procedure, we can derive quantum codes with linear distance and constant rate using a random construction. Yes.
Yingkai, there's some questions that ask, so if you go one slide back to slide 9, then it is not clear, or people are asking whether it is clear that the columns of the A matrix are linearly independent.
Whether it is clear they are linearly independent.
Yes.
It is not clear a priori from this construction. So this, as some of you may have noticed, this bound over here is not a tight bound for showing that there is a null space, a non-trivial null space in this A matrix. So you could potentially have a matrix with fewer columns than rows, and which still has a non-trivial null space.
Okay, thanks.
Thanks for the question. And I'd like to then move on to the next part, to the next question. So recall that in the previous slide, I've said that we can design quantum codes by checking the feasibility of linear programs. But what if, but the question you may have is, what if the linear program is infeasible? well, you could just you could say, well, I'm just going to pick different subsets of the code words, but maybe you're not pleased with such an approach. So so if you're not pleased with such an approach, then we can use we can appeal to this approximate quantum error correction procedure, where you don't need to rely on the feasibility of linear programs. So the idea is this: really, all that the bit flip distance is inherited directly from the classical code. So all that we need to do is to check the non-deformation conditions, which is how we can correct the phase errors. And the non-deformation conditions basically look like these codeword sandwiches. They are really, each of these sandwich, you can imagine it to be a high-dimensional vector in a high-dimensional space, where the number of dimensions is labeled by the Pauli error P. And having the non-deformation condition satisfied means that all of these sandwiches are equivalent to each other in this high-dimensional space. Well, obviously, if you're going to pick well, all these codes in a very ad hoc fashion, you wouldn't have the sandwiches all lining up to be equal to each other in this high-dimensional space. But the packing argument is that if you pick enough of these points in a high-dimensional space, there will be some epsilon ball around which you would have a sufficient density of these points. And from these points that have a nice overlap, you can design an approximate quantum error correction code where the approximation error would be the size of this epsilon ball. So this is approximate error correction if we don't want to worry about linear programming. And so coming back to the question that was raised previously, okay, so we have this framework for taking any classical code to a quantum code. So you may wonder, okay, so what if we take the most obvious classical code, the repetition code, and we demand that it has a distance of, say, 2. And if you use our formalism, you would find that the null space of the matrix has a dimension of 0. So there is no quantum code that you can get from the repetition code in this formalism. So there's no free lunch. Repetition codes are not good enough. What we find very interesting is that if you take this Hamming code, the 743 Hamming code, and you apply it to our formalism, we will get a matrix for which the null space has a dimension of exactly 1. And so we recover the Steane's code uniquely. And I like to point out that for this particular A matrix, it is not a wide A matrix. It is a skinny A matrix, and it has many more rows than it has columns. We can also put as input a non-linear code. So we put a non-linear cyclic code of length 4, and we are able to get a CWS code. So that's interesting. And we like to emphasize that our formalism is not just restricted to designing quantum codes that are superpositions over computational basis states. We can also have other basis states, such as so-called Dickey states, which are uniform superpositions over classical codewords of constant Hamming weight. And we can design permutation invariant codes using this procedure. So this brings us to the next part of the talk. So there has been a very long history of designing quantum codes that fit within the ground state or the approximate ground state of realistic Hamiltonians, dating back to the seminal work of Kitaev, where you try to put a quantum code in the approximate ground space of a honeycomb lattice with nearest neighbor interactions, where the interactions are XY Heisenberg interactions. And this type of investigation has remained active till today, where there have been attempts to find quantum codes that reside within the ground space of the XY Hamiltonian on, say, a square lattice, and this also known as the compass model. But what we find most interesting is the idea of engineering a Hamiltonian to suppress noise, because one could ask the question, why do we even need to bother with the Hamiltonian if we want to have a quantum code? We can just have a quantum code as is. And the intuition is as follows. If you have a Hamiltonian and you imagine that it has many terms inside, many local terms, and you imagine that each of these local terms is like some barrier over here, and you imagine that this is like some racetrack. The noise is like a racing car. It's trying to get to your code. It's trying to race to your code and destroy it. All right. So if you have no terms in your Hamiltonian, there are no barriers here, and then the racing car will very easily race to your code and destroy what's there. And the barriers will, in some sense, help to impede the speed at which the errors destroy your code. So by having more and more terms in the Hamiltonian, we have more and more inherent resilience against errors. And even if we cannot protect against all types of errors, if you could protect against all types of errors, inherently you would have a self-correcting quantum memory, which is known to be very challenging to implement. One could hope to have some sort of resilience against noise in one basis, for example, which is relevant in biased noise models. So we find we were inspired by a related work, which is by Bravyi-Terhal et al., where they designed quantum error correction codes in translation invariant spin chains. So in this work, what is most important is that they try to embed quantum codes in approximate ground space of of translation invariant Hamiltonians. And in a nutshell, what we do is very similar, but we improve on the work in many aspects, and we fit our quantum code exactly within the ground space of the Hamiltonian. So now let us share with you what our quantum code is. But first, we start from the Hamiltonian that we introduce. It has two local terms, the P terms and the Q terms that we show pictorially over here, and it has some one local terms that penalize the occurrences of the zeros in the ground space. And so the Hamiltonian is given by some one local terms plus some two local terms. The two local terms have some physical meaning. They correspond to spin transport, namely the swapping of 0 and m, and also spin interaction, where 0, 0 can turn into m and minus m. But what is most important is that we were able to analytically solve the ground space of this Hamiltonian. And what we find is that the basis states of this Hamiltonian correspond to classical bit strings with some feasibility constraints. And from these feasible product states, we're able to apply the formalism of the first part of the talk to get quantum codes. And in fact, we are able to show that there are linear distance codes that reside within the ground space of our Hamiltonian, which is the result over here. And this is shown pictorially. We show this pictorially in this graph, where the y-axis is basically a lower bound on the null space of this A matrix. So if this is very large, that means that we surely have quantum code. And we have quantum codes all the way up to correcting up to 4% of the errors. So this shows that we have a linear distance, one from a random construct and one from an explicit Justison construct over here. And we were able to design explicit 8-qubit code over here. It's a very nice structure. It has a concatenated structure with the outer codes and the inner codes. And we also have error detecting codes with very nice structure. And this brings us to the last slide, where we thought about whether we could call the quantum codes that we found a quantum LDPC, but then we thought no, because it doesn't. Our codes do not occupy the entire ground space. It only occupies a subspace of the ground space, and that's why we might call this the subspace LDPC code. And we can look at our codes in context of the Bravyi-Terhal no-go theorem. This sidesteps that because we relax the stabilizer constraint, and we are also in the subspace of the ground space. And our code is different from the previous approximate quantum LDPC in that ours is too local, and exact, but then with the caveat of lying within a strict subspace. And we would have a topological order in 1D, if not for the fact that we didn't use all of the ground space. And with that, I thank you for your attention, and I welcome questions.
Thanks a lot, Yingkai, for this very nice talk. So there are a couple of questions around. So the Slack is very active. Thanks a lot. So we try just to cover some of them until we hit the time deadline. So there's another question going on discussed by Markus Grassl and others about something similar that I already asked about this A matrix. And sort of the question was, is it obvious that there exists a non-trivial solution just because, or just by assuming that the matrix is flat? Is this obvious?
It is obvious. This is a known fact in linear algebra. Basically, if you have a real matrix and it is wider than its tall, then it must have a non-trivial null space.
Okay. Fine. Then maybe we can continue with a much broader question. So somebody was asking about intuition or an explanation why it is desirable to fit quantum codes in a ground state of some Hamiltonian.
Yes, thanks for that very interesting question. And over here, I was drawing this this cartoon. I was alluding to this cartoon over here. And the idea is that if you have a Hamiltonian and it has terms that appear inside, then if you have local errors that are going to appear, that would like to appear, they will have some chance of being energetically penalized by the terms that appear in the Hamiltonian. And hence, if that local error appears, you would incur some energy penalty, and because of the energy penalty, it becomes less likely to occur. So this is the intuition. Of course, if our code occupied the entire ground space of the Hamiltonian, it would suffice to prove the gap of the Hamiltonian to obtain a resilience, a natural resilience against these all types of errors. But what we like to emphasize that even in a case when you are occupying only a subspace of the ground space, these energy penalties also can kick in to help us.
Okay, maybe I pick a last one, and then I already apologize for all the questions that are interesting that were asked in the Slack that we cannot discuss here, but Yingkai, I'm sure you're happy to answer them later. So somebody was asking whether there's a natural way to extend the formalism you presented beyond Pauli noise, and if yes, to what kind of models, for example, anionic systems or something like that?
Yes. So I believe this question is alluding to the first part of the this A matrix construct, and this. And I'd like to emphasize that this goes beyond Pauli noise. In fact, when we talk about the distance of a code, it doesn't have to be restricted to Pauli's, but then from the theory of quantum error correction, we know that it suffices to check these sandwiches, these non-deformation conditions for these Pauli's, because the Pauli's form a nice basis for the space of errors. But of course, if one wants to go beyond the notion of a distance for the correctability of errors, we can indeed also specialize, we can also adapt this condition to introduce other types of noise, such as amplitude damping. And that is certainly possible.
Cool. Thanks a lot, Yingkai, for the great talk.
Thank you.